Okay, welcome everybody to today's lecture. This is the 7th lecture, isn't it, about physics of semiconductor devices. Tomorrow we will have, remember, the 3rd tutorial on Pin Junction. And today we're going to finish what I wanted to tell you about Pin Junctions. Just before we get started, as I mentioned in one of my announcements, I would like for those of you that are available after the lecture to go to LTC, RBB LTC, just above us, to have a brief chat with anyone that is interested about the to improve, you know, the submodule. All right. We can do it then another time. Would you prefer? I mean, it doesn't really matter how many are there. It's not compulsory. It's just, you know, to have a chat so that I understand exactly what can be done, what we can't, and such. Is there any other time you would like to do that, or?
What about next week?
Next Tuesday.
Yeah, is that okay with everyone else as well? Yes.
Is next Tuesday good for everybody?
I thought I might not say something.
Okay, yeah, we can do it next Tuesday. There is no rush. You know, it's more about trying to see if we can sort some of the things out now. You know, that have been mentioned in the midterm survey that I did the last Wednesday. Okay, so for today, what I wanted to do is there was in the plan there was another application of Pin junctions, which would show you effectively how to use it to make a proper AC-DC adapter, what you use to charge your mobile phone, let's put it this way. In the circuit application I presented last week in the post-lecture video, there was a hint to that, the initial part. And in this, you know, this other circuit application, it would show you how to use the Zener diode to further improve, let's say, things in that direction. So, but I don't want to do it here because it's a bit technical. There is no reason to take time from the lecture, and this, you know, for curiosity. So I'll leave it for the post-lecture video. So today, in here, we are going to look at some, let's say, developments around the Pin junction, which is the LED, the light-emitting diode, and photodiodes, together with, which is strictly related, solar cells. Okay. So LEDs, emitting lights, and then everything else that is related to absorbing light and transform it into some sort of signal, electronic signal. So the two opposite processes, let's say. Okay, so let us start with probably the part that there is not too much to talk about, which is the LED. The photodiode, let's say photodetection, we have a lot more to say, as we will see. Also regarding photodetection, photodiodes, solar cells, and everything else that is related to absorbing light. We will see. I wanted to show you also another application regarding photodetection. Under photodetection, we put, for example, photoconductors and photodiodes. These are the two simplest devices that we could talk about. Photoconductors is something that I briefly mentioned when we looked at generation recombination. So there was an application that I put in the post-lecture video about that. So again, as photoconductors is something that is kind of like an application, I will leave it for the post-lecture video. But photoconductors also fall, which is basically a piece of semiconductor, fall into the category of photodetectors together with the photodiode and so on. The solar cell is just, as we will see, a photodiode specialized, to the generation of electricity in that way. Okay, so the LED. So the first thing we need to clarify in our mind some definitions of some important quantities. The first one is the so-called internal. When we talk about light emission processes, we need to define precisely what is the internal quantum efficiency. Remember, we are talking of the LED. So light emission. So what is the internal quantum efficiency in light emission? We indicate this quantity with eta for internal. And in practice is the number of photons emitted in the active area of the device divided by the number of electron holes that are recombining. So the number of photons emitted, so radiative emission emitted in the active area of the device divided by the total number of electron holes that are recombining. So we could also define it as the number of radiative recombination events divided by the total number of recombination events. We had briefly seen already the concept of internal quantum efficiency when we were in chapter 2, when we presented the light-related phenomena in semiconductors. And I had actually given already this definition. At that time, I used the definition as probability of radiative decay divided by the total probability of decay. All these things I've said are all equivalent. Okay? So I will just put here the number of radiative recombinations events divided by the total number of recombination events. Okay, but as I said, you can define this in many equivalent ways, as I said. Probably the one that we will repeat also later on is the one that I mentioned at the beginning, the number of photons emitted, because these are the number of radiative events, divided by the total number of recombination events is the total number of electron hole pairs that are recombining. Okay. The other quantity we want to define is instead the external quantum efficiency. which we indicate by eta E, or E, small e probably, eta E. Now, the difference between this and that is that eta, the external quantum efficiency, takes into account, contemplates maybe the possibility that not all photons will make it out. Some will be reabsorbed. So effectively, we could already, so the external quantum efficiency, if we wanted to use, the definition we said previously, number of photons emitted divided by the number of electron-hole pairs recombining, we could simply, here I had to specify the number of photons emitted in the active area. Sorry, I need to specify this. In the active area. So there where they are being generated. While here, what I would do, I would use the same definition, but without that are actually coming out of the device. So the number of radiative events and that come out of the device, that's what I mean. Or radiative events, recombination, I forgot recombination. Recombination events divided by the total number of recombination events. So what this does is, as I said, contemplates the fact that not all photons will escape from the point where they are generated inside the semiconductor. And so we can actually write this as the internal quantum efficiency multiplied by a fraction of that contemplates this fact that not all, a fraction of the number that represents the fraction of photons that are extracted. This is the so-called extraction efficiency. And in general, the external quantum efficiency is obviously smaller than the internal one, because obviously this is not 1, is smaller than 1. And for example, the external quantum efficiency, for example, could be 0.2, so 20%, while the internal could be, I don't know, 50%, 0.5, these kind of things. So this is really general when we talk about light emission. Okay, the light emitting diode is a Pin junction. Nothing more, nothing less. It's simply a Pin junction where, though, all extra care has been taken in such a way that you remember, in semiconductors, we have two types of recombination, radiative, non-radiative. So extra care has been taken in such a way that any recombination taking place will be mainly radiative rather than non-radiative, okay? So that's what a Pin junction is. And obviously this means already, as we know, that one important thing to choose properly is what? There are two types of semiconductor. That must be direct. That's already a very good starting point. It should be direct, isn't it? If you want to have, a good efficiency. Okay, so this means that we already know the IV characteristic of a Pin junction. So the IV characteristic is the one we have already seen for the Pin junction. So for my LED, I'm expecting a characteristic like this, where I is equal I0 e to the EV over KT minus 1. And what do we expect? How is it that this Pin junction is emitting light? Can we express this on a diagram, let's say on the energy diagram of my Pin junction? If this was my Pin junction, my LED. So if I wanted to draw an energy diagram in an attempt to kind of show, how is it that this thing is producing light? So we could show the energy diagram of my Pin junction in slight forward bias. So forward bias means this is the N side. Well, yeah. So the N side, so this is the conduction band and the valence band. Slight forward bias means the Fermi level should be slightly lower here. And this is the something like that. And maybe, so remember the story that here, in this situation where we have a slight forward bias, QV, we still haven't, V is still smaller than VBI, but we saw when we did the Pin junction that there is a current already in this situation that is flowing that way. If you remember, this situation is one of the intermediate ones we considered. It was when we were trying to understand all the possible processes qualitatively. If you remember, we had done this kind of these energy diagrams, several of them. The story was here we have many electrons, if you remember. Here there is a slight slope like that, so there is this means that there is still an electric field that goes like that in this point. Nevertheless, and here there are very few electrons because this is here they are my minority carriers. So some of these can still diffuse, go against the electric field, and so that's why we have a large current like that. And also here the holes can go like that. And so what is happening really is that these carriers, the electrons here, that they move in this direction, let me remove this arrow, they actually combine at this point and they emit light. So that's what is happening. When we looked at light emission, back when we did semiconductors in chapter 2, we also discussed how should the spectrum of these photons emitted by the semiconductor look like? How are they distributed? And there we concluded, if you remember, that the energy of these photons being emitted is actually roughly Eg. And the distribution is such that the full width half maximum is very narrow, is 2 kT, roughly 2 kT. 2 kT is very small, remember. kT as an energy in terms of EV is 26 millieV. So we are talking of a very narrow distribution. So if I was to plot it, and this is Eg, this would look really sharp. The full width half maximum is very small compared to Eg. Eg is the band gap of the semiconductor, which is, I don't know, if it was germanium, is 0.6 eV. Do you remember the reason why this is true? When light emission from a semiconductor in the end happens always very close to Eg. Because if you remember the story of the conduction and valence band, when you promote, if this is E, K diagram, we have, say that I am promoting an electron that was here, I'm promoting it up here. Okay, so now the electron goes up here. This loses its energy very quickly through collisions with the lattice, and so this is called thermalization. Go back, if you don't remember, to that part. And effectively ends up always at the bottom of the conduction band. The same here, when the electron has been promoted, this is left behind a hole. The hole as well will thermalize. So in the end, the electron-hole pairs that were left behind after the electron was promoted, they end up always being there. And so when they recombine, the energy is always roughly Eg. Okay, so that's the reason why in light emission we have a spectrum of the photons that is always around Eg. Okay, so this is really briefly the fundamental stuff about my LED. Few more things to say. Yes, a lot of effort, as you understand, goes into making eta extraction as close to 1 as possible. And these extra efforts go in two directions. The first one is this. So up to now, we represent the pin junction in this way. Two pieces of silicon, different, attached together, okay? In reality, what we do when we make pin junctions is we take a piece of silicon, of semiconductor that is N, and we make, by implanting dopants, this part very highly p-doped. This creates the p junction here. You can see that this is the interface represents the where the depletion region will be created effectively. So if I look at it now in this way, I put a contact here and a wire here. This is my P terminal, and this is my N terminal. I've made the P junction, or the LED, or the photodiode, whatever. Okay, they are all P junctions. So, as we explained here, light is being generated around the depletion region, there where the carriers recombine. So on this plot, light, the source, the active area where light is being generated is all around this interface where the depletion region is. So you understand that. Let's consider this point here. So if a photon is emitted here, this will go in every direction. Okay, some of them will come out. Now, there are several problems here. And this is where I go, because remember, I'm saying this because how do we make eta extraction as big as possible? So people, what people try to do is to bring these, the active area as close as possible to the surface, not to be too buried inside the semiconductor. So this is one thing that everyone has to try and do if you want to increase the chances for the photons being generated in this area to come out. But there are obviously some physical constraints. So the first one is that this is a semiconductor, and this is, let's say, air. So the refractive index here is larger than that. So if a photon here is emitted in a certain direction, what might happen to that photon? When it goes from a refractive index into a small refractive index. Sorry? Yeah, total reflection. So there will be a cone of light. So there is a cone on each point. Only the photons that are emitted within a certain angle can escape. All the others will undergo total reflection. This is the first problem, total reflection. And once they are reflected, they will go back into the semiconductor. It's very likely that they will undergo Auger absorption. That is, they will give back their energy to an electron, which will be transform all that energy into kinetic energy, and then end up in the end as kinetic as heat. Okay, so whatever goes out of the cone of light is effectively turned into heat. So total reflection is one process which ends up in the end also in being transformed into heat, or directly also, remember, Auger absorption is always there, so there is always chances that this photon being directed, emitted in that direction, is absorbed by an electron and then is turned into heat anyway. Okay, so there are all these things to take into account to maximize this thing. So this is one point, what someone needs to consider to maximize the extraction efficiency. And obviously, in this equation, let's say eta E equal eta I, eta extraction, eta I depends on the semiconductor. So as we said, how good is the semiconductor? All our attempts to make sure that recombination is mainly radiative rather than non-radiative. So there are some actions to be taken on the semiconductor to make sure that this is as high as possible. What are these actions? As I said, first of all, the semiconductor should be direct. That's best. The second thing, for example, try to make sure what makes non-radiative recombination high. As we said, the presence of defects. So you need to make sure that in your structure around the depletion region, there are as few as possible defects, because they will act as non-radiative recombination centers, and so they will decrease eta I. So there are all a number of actions that need to be taken to make sure eta I is high, as high as possible. Regarding eta extraction, there are these problems. So try to bring the emission point that are all around the depletion region as close as possible to the surface. And on top of that, there is also another factor that the extraction efficiency will actually also depend on the angle. So there is a very nice, that I will try to show you now. There is actually a very nice plot or figure. So you have to imagine that these, screen down. So this is on one of the references. Now, this LED, this piece of semiconductor, Pin Junction, must be protected from the environment, so it must be encapsulated. So another thing that is very important to maximize eta extraction is that eta extraction depends also on the angle. And the reason it does is because depending on this encapsulation, the photons are being emitted with different probability in the different directions, just because of refraction. And so you see that if you were considering, this is the active region, let's say the point where the pin junction is, the actual piece of semiconductor that is emitting photons. And this is the shape of the encapsulation. So if it was flat, and you were looking at, this is the far field distribution intensity of the photons, okay? Far field means that you are, the dimension, this point becomes a point source effectively. That's what it means, far field. So when you are considering this type of geometry, flat, the distribution of the photons is this one here. So this means that if you were looking I don't have much space here to show anything, but so this means that how do you read this plot? If I was analyzing with the intensity I perceive on the vertical, so here I'm assuming this is 1, for example, as you can see, 1. Then as I move to a certain angle, the corresponding intensity is falling. And if I go to 90 degrees, I'm getting nothing. That's what this means, how you read this plot. Okay. If then you change the shape of the encapsulation to hemispherical, suddenly you go to this, which is, this means the same distribution of photons everywhere, no matter the angle you are looking at the source. Okay, so this means that with this geometry, if I was looking the source from here, I would get the same intensity of light as the one that I would get from here. Huh? And finally, if I was to use a parabolic shape, you would get, this elongated, let's say, distribution. So as you can see, you get a very high intensity when you are just at the top, while when you, whatever other angle you are looking at, more or less you get 0.2. Well, no, it changes a lot. So, but it's never really 0. Even when you are at 90 degrees, so looking at it like that, you still get a 0.2 of the total intensity that you were getting here. So this is just to show you that you can manipulate a lot this quantity here, and also how the photons are distributed. Okay, we can take this off now. So, let me do something here. We don't need this anymore. So, for the LED, what we can say, based on the things we've talked about, is this. Based on the definition we've given of the external quantum efficiency, we could say that the external quantum efficiency is I could write it like that, and tell me if you agree. The number of photons per second divided by the number of electron-hole pairs per second, which I would translate, as we said, the number of photons generated per second, and divided by the number of electron-hole pairs that are recombining per second. And this can be written. The bottom is easy. The number of electron-hole pairs that are recombining is the current that is flowing through the device divided by the elementary charge. If I do that, the current is charge per second, and so if I divide it by the elementary charge, this will tell me the number of electrons or number of holes or positive charges that are being injected into the device, and so this will also tell me how many are recombining. And well, for the number of photons per second, I can define it, can write it as the photon flux. Remember, the photon flux is the number of photons, in this case, emitted per square centimeter per unit area per unit second. So I need to multiply by the active area, or the emitting area, in order to make it photons per second. And based on the definition of these quantities, the light-related quantities, the photon flux, we can also write this numerator as the power of the beam being emitted, this is in watts, divided by the energy of the photons being emitted, divided by I over E. So this is a nice compact formula that we come up with. And the last thing to mention about the LEDs is that, so this is the external quantum efficiency. And the other thing is that we can define is the power efficiency, which we indicate with eta P. So this is the power efficiency. Which obviously is the power that we are, the electrical power we are sending to the Pin junction, which is V times I, isn't it? V and I are the voltage I've applied to the Pin junction, and the I is the current that is passing through that is being recombined to generate eventually some photons. And on the numerator will be the power of the photons being emitted. So based on this realization that the external quantum efficiency is this quantity, we can write eta P in function of eta E, and obviously this means that this is this stuff here. This is E times V. Oh, at this point, this is actually roughly eta E. So these two quantities are actually more or less the same. Here, obviously, what I haven't told you is that these two are more or less the same. And the reason is that, as you can also guess from here, when the Pin junction, the LED, is forward biased, the quantity EV, QV, well, yeah, QV in general, is roughly very close to QVBI. The current grows a lot. So more or less, we know that when it's forward bias, the voltage we are applying will be very close to VBI anyway. And we can show, as we've said previously, the photon energy is roughly EG, and EG, this is what we demonstrated it, we mentioned maybe it when we did the Pin junction. EG is very close to QVBI. VBI, if you look at the, if you remember the Pin junction in thermodynamic equilibrium, I'll do it here. So if you remember, the Pin junction in thermodynamic equilibrium looked like this. This is the Fermi level, conduction band, valence band. And VBI was, this was QVBI. So as you can see also from here, if QVBI is defined as the difference in the conduction band between the P and the N side, or the valence band is the same. But this quantity is very close to the band gap. I'm doing it now with my with my fingers here, but you also can see it for yourself that VBI is indeed very close to, and this is because this side is P, very much P, this is very N, And so the Fermi on one side is very close to the conduction band, on the other side is very close to the valence band, and that's the reason why VBI is very close to the band gap, okay? So on the numerator here, the photon energy is very close to QVBI. On the denominator, this also, when the Pin junction is forward biased, is roughly EVBI, and so that's why this justifies this conclusion. So the power efficiency is very close to the external quantum efficiency. Okay, so that's all I wanted to tell you about the LED, just so you don't think it's an alien when you encounter one. And let's go to the next part, the second part. We'll probably dedicate the rest of the lecture today about that. And this is the photodetectors. Now, as I briefly mentioned, photodetectors, well, we will go through some definitions very similar to those. The first photodetector would be a photoconductor, so based on a piece of semiconductor. As I said, I briefly already touched that some time ago, so I want just to add some conclusions, let's say, based on the new things we've learned. But I'll do that in the post-lecture video, just out of curiosity mainly. I want to focus here on the more important photodetectors that is interesting for us, which is the photodiode. So let's have a look at the photodiode. So first of all, so these were true for the LED. Something similar, simply we need to reverse numerator and denominator, will be true now for the light absorption processes. When we talk about photodetectors, we are now interested not in light emission, but in light absorption. So for light absorption, how do we define internal quantum efficiency? So internal quantum efficiency is the total number of electron-hole pairs created in the active area divided by the number of photons that are reaching the active area. So I need to swap things effectively here. So it is the number of photons, number of electron-hole pairs created in active area. I need to specify that. Divided by the number of photons that reach the active. It's important because this is the internal quantum efficiency. So I'm testing only what effectively the semiconductor does, and I'm not being influenced by any other external factor like geometry, other stuff. The external quantum, let's stay on the internal. So we know already something that could point us, let's say, in this direction, and that's what we call the absorption coefficient. We said that the absorption coefficient is the probability that a photon is absorbed, which means we'll create an electron-hole pair per unit distance. So this means that if I was dealing with a piece of semiconductor of thickness d, and my photons are hitting the semiconductor, and I know that the semiconductor has an absorption coefficient alpha n, then alpha times d would tell me the probability that each photon has to be removed from the beam. That means to create an electron-hole pair. So this means that this quantity is actually eta I. This is now probability that a photon creates an electron hole pair. And so that's what eta I is, isn't it? The probability or that a photon creates an electron hole pair. So remember that there is in photodetection there is this intrinsic connection between the internal quantum efficiency and the absorption coefficient of the material. Remember that alpha depends on the energy of the photon. And alpha depends on the properties of the semiconductor, like band gap energy. Okay, so all these things that we know about alpha are now heavily imprinted into eta I. Okay, eta I now carries a lot of stuff about our semiconductor. Obviously, because of this now tight relation of eta I with alpha, this means that again, direct semiconductors are better than indirect semiconductors in doing photodetection. Okay, let's go to external quantum efficiency and then we have a break. So we need to modify this definition as well. So the external quantum efficiency is obviously related, as previously for the LED, is obviously related to eta I, to the internal. And simply the only thing is that it contemplates the facts that not all electron hole pairs will make it out of the device and generate some current. And not all photons from the outside will make it to reach the active area. So basically, I will write everything again and remove the active area from the sentence. So is the number of electron hole pairs created here, I mean that I sense them externally outside of the device. This means that are able to create or maybe participate to total current. That's what I mean here. Divided by the number of photons number of photons. Let me put in parentheses, hitting the device. So obviously here what we are saying is that eta I, as we did also previously, contemplates the fact that some electron hole pairs do not make it out. So eta I will be, for sure it depends on eta I, but there will be only a fraction of the electron hole pairs that are, we use this term, collected out, that make it out. So I have an eta, a fraction of collection, call. So there is only a fraction of these electron hole pairs that in the end participate in the total current that I will see outside of the device. This is the collection efficiency, is called. And the other one is that not all photons that are hitting my device will make it to the depletion region, if it was a photodiode, where the absorption will take place. And so there is it's called eta T, transmission efficiency. And so here eta external quantum efficiency eta E is made of these three terms. And it again, as previously, eta E is obviously smaller than eta I. And for example, I don't know, 0.15 and I don't know, 0.7. 15% external quantum efficiency and I don't know, 70% internal one. So this kind of differences. Okay, let us have a break here. It's 14:52, so we start at 15:02.